Intense activity below ground. The tunnel builders are working around the clock for a major project on behalf of Deutsche Bahn. In Stuttgart, they're blasting 20 meters beneath the city in order to clear the way for the tunnel. In this job, there is no such thing as routine.
Every blast is a special event.
And even on the surface, the tunnel builders are faced with great challenges. The most important component of a tunnel boring machine has to be loaded, but the gigantic crane is refusing to budge.
I don't know, the brake won't release. Not sure what it is.
The crane is broken.
Tunnel construction can produce some surprises both above and below ground.
Improvisation is the name of the game so that the huge tunnel boring machine can finally start its work. The new ICE rail line from Wendlingen to Ulm. At over 8 kilometers in length, this is where one of Germany's longest tunnels is to be built. Directly adjacent to the A8 freeway, 2 huge tunneling machines are waiting to be put into operation. They've been christened Wanda and Sibylle. Tunnel excavation below ground is referred to as driving. In this case, the loosening of the rock under cutter head wheels. They're the most important part of a tunnel boring machine. Very soon, they will be digging through the earth with their 140 spade cutters. The cutter head wheel is situated at the head of the tunnel boring machine and works its way slowly forward. It rotates at 2.7 revolutions per minute and is forced against the bedrock at a pressure of up to 400 bar. This allows the high-strength steel disc cutters and spade cutters to loosen up to 20 meters of rock per day. The cutter head wheels have a diameter of almost 12 meters and each weigh around 200 tons. Now, a crane will raise them across the construction site to the heads of the tunneling machines. There, they are then secured into place, flange on flange, with great precision. The mounting process for Wanda's cutting wheel was completed successfully a few days ago. Final preparations are now underway to ensure that Sibylle also receives her cutter head wheel. Everything now depends on this construction crane. It weighs 1,200 tons and is 90 meters tall. A veritable steel giant. Crawler cranes of this kind are rare in Europe, so every day is very costly. Even the delivery was a complicated affair. 50 truckloads were necessary in order to get all the individual parts in place. The crane was then erected on the construction site. The assembly took 5 weeks. It plays the key role in today's loading operation. It's set to very carefully hoist the second cutter head wheel into the construction pit. Jens Klassen is the technical director of the construction firm and oversees this spectacular step.
The crane operator is the most important person here today. He has to ensure safety at all times. This large crane is a sophisticated piece of equipment, and so he has to ensure that all units are working. Ultimately, he's responsible that nothing goes wrong.
The cutter head wheel has to be properly secured before the lift can begin. For this, the workers attach massive eye hooks onto the corresponding mechanisms on the cutter head wheel. 60-kilogram iron bolts secure the connections. Not an easy task.
Da de Bolzen rein, rumziehen. Bisschen länger nach hinten. So, jetzt zieh rum. Jetzt hoch. Bisschen hoch. Gut.
First of all, the cutter head wheel has to be set upright. Time to see if the workers have done everything correctly and all the bolts hold up. Now, the narrow safety covers on the flange connections have to be removed. Then, stage 1 of the loading process may begin. The cutter head wheel rises slowly. Nearly 200 tons of steel are attached to the cables. Now it's suspended in the air for the first time, the gigantic centerpiece of the new tunnel boring machine. A smaller 500-ton crane helps to raise the cutter head wheel into the correct vertical position, so that the huge crawler crane can heave it into the construction pit. Before mounting it into position, the cutter head is rotated 180 degrees for a final clean and inspection. Everything has to be just right for the next maneuver, one of the most intensive of the entire construction project.
Huge components with heavy loads are being assembled in intricate steps. Always a special highlight. It somehow gives the finishing touch to everything. And it's always impressive when such a huge component is lifted into position. It's a unique sight.
Soon, the cutter head wheel will be working in the ground, creating up to 20 meters of tunnel daily. Construction of the Albvorland tunnel has been calculated to take 18 months, provided nothing unforeseen occurs. But even today's inspection is already taking longer than scheduled.
It's going to be tight if it's 200 metric tons.
I don't know, the brake won't release, not sure what it is. We can't start yet because we have a small problem. The large counterweight there at the rear has to be swiveled out with the crane simultaneously. There's a minor electronics issue which we need to resolve.
This ballast trailer, loaded with steel components, is firmly connected to the crane. It acts as a counterweight for stabilization purposes during the lifting operation. There's a lot of activity at the moment because it's not rotating with the crawler crane as intended and is jamming. New solenoid valves might help.
Hopefully it's that.
As with all electronics problems, you have to find out what it is first to be able to resolve it. That's what we're currently working on. With problems like this, it's the fault investigation that takes up the most time. Fault clearance is then a relatively swift process.
The fault investigation process is indeed proving to be very problematic. And as long as there is a problem affecting the ballast trailer's movement, it's not possible to begin transporting the heavy cutter head wheel. The workers look for a solution.
Yeah, give it a go.
Yeah, okay.
The crane operator is able to simply start up his huge machine as often as he wants. However, the onboard computer continues to prevent a lift and stops the operation. This would be too dangerous if the counterweight failed to actually swivel out. The ballast trailer's brake is still disabled. The crane's electronics will not permit a lift. Since a crane of this size cannot readily be replaced, the engineers have to wait for an express delivery, which will bring spare parts during the night. However, no one knows for sure if it will work then.
The crane is broken. The crane company has one operator, which generally has its own repair team. And they've been called. Yeah, for a crane of this size, it's a difficult thing, so they'll come right away and start repairing it.
It's a good example of how tunnel construction can produce surprises both above and below ground, but for safety's sake, we must simply guarantee that nothing happens here.
The workers have no other option than to postpone the lift, acutely aware of the significance of the delay.
Well, a crane like this costs several thousand euros a day, and so we also lose time here when it comes to the installation. We can probably make up that time again, but of course the crane is charged on an hourly basis, and so it costs a lot.
The loading of the cutter head wheel definitely is overrunning. Plus, there are additional challenges too. The Albvorland tunnel is not the only tunnel being worked on as part of the major construction project. So that the ICE can travel at high speeds, it's set to pass through tunnels on more than 30 kilometers of the stretch of the network around Stuttgart. One of the construction sites is located directly beneath Stuttgart. From here, tunneling work is being undertaken in different directions. This work is being done in part via cutting tools and excavating, but mainly via blasting. For the Austrian tunnel construction team, there is only one entry point, and it leads through this deep shaft.
This is the bottleneck of our construction site. From this shaft and the ensuing access tunnel, we are working on 3 drives simultaneously. We're now already almost 3 kilometers in one direction, 1.5 kilometers in the other 2 directions. And we supply our entire construction site via this shaft.
In order to access the excavation sites, we can go down in the lift or take the emergency stair tower. When all the tunnel work has been completed here, this access shaft will be filled in again. But for now, it's a hive of activity.
The shaft has a depth of 40 meters and a diameter of 22 meters. All the materials have to be brought in here, and this includes the support means: steel mesh, lattice arch girders, rock bolts, and spikes. And even the shotcrete has to be brought in through here. In particular, the excavation material has to be transported out of here. In the background, we can see our debris collector. Our portal crane that lifts this dumpster can lift 60 metric tons. The dumpster has a dead weight of almost 10 metric tons. Consequently, we are able to carry a maximum load of 50 metric tons with a dumpster.
50 tons. This corresponds to approximately 2 truckloads. 50 to 60 dumpsters are lifted out every day, full of excavation material or spoil which comes from the blasting or excavation work. As this material is being removed, the 100-meter-long access tunnels provide entry to the cutting faces. Machines and vehicles are deployed here, which are specially designed for deep mining.
Once we have 3 drives running simultaneously down here, we will have more than 50 big units down here. For a cycle, we need a jumbo, a lifting platform, a wheel loader, an excavator, a mobile shotcrete machine, and a mixer truck to transport concrete. All these machines are especially designed for mining or tunnel construction.
The journey initially proceeds through the one-way standard tunnels. Here, it's a mere 10 meters from the roof of the floor, or, as they say in tunnel construction, from the crown to the invert.
Here in the final 140 meters, we have enlarged the tunnel, meaning we have made the tunnel higher and wider. This allowed us to be able to branch off a further 2 tunnels, as there was so much room at the end of the 140-meter section. The left tunnel tube, which we can see here, leads to unter Kirchheim, and the right one goes to ober Kirchheim.
In one of the tunnels, on what will be line 714, boreholes are prepared for subsequent blast. This work is mainly carried out by a skilled Austrian workforce. Austria has a tradition of tunnel construction. This construction site at the end of the tunnel is known as the working face. This working face is situated directly beneath the Neckar River. Therefore, the tunnel worker with his 2-armed drilling jumbo needs to take a few things into consideration: rotation speed, hammer pressure, water pressure, and oil pressure, as well as drilling depth.
The biggest challenge is being accurate in terms of the next excavation, so that the next steps can also proceed quickly. Because additional underground excavation work is taking place.
There are special static conditions in urban areas or directly beneath rivers. As a result, a very short ring closure has to be completed. This means that in the first instance, almost 1.5 meters is blasted out of the upper semicircle of the future tunnel, the upper ledge known as the calotte, and immediately after, the lower section known as the pit face is tightened and secured. This process is known as conventional excavation. Once the almost 100 holes for the explosive devices have been drilled, a wheel loader levels out the ground to assure the workers a secure footing. Next, the demolition experts arrive with a full load of detonator fuses. To carry out a controlled explosion for the removal of 1.5 meters of earth, they need approximately 90 kilograms of explosives. The primer cartridges have to be inserted with detonators into all of the designated boreholes.
It is inserted and tamped that it abuts on the borehole recess. Of course, the detonators are graduated to ensure a good blasting result and limited vibrations. Since we have some buildings up above, we also need to take vibrations into account.
The tolerated vibration level for every house on the surface has been determined beforehand. Landmark buildings differ, for example, from post-war buildings or industrial developments. The people on the surface will also feel any explosion down below.
Well, it does wobble a little. But it is certainly not possible to trigger an explosion down here so close to the buildings, so close to the foundations of the houses without it being noticed above. We are not allowed to carry out any explosions at night here, for instance. A ban on blasting is in place between 10 p.m. and 6 a.m. Here we have approximately a covering of 20 meters to the surface. The houses will, of course, feel the effects of these blast shocks.
So, at night, the team uses a cutting tool to extract the solid mud rock. This process takes 3 to 4 times longer. There is no better option. Consequently, blasting work continues for as long and as often as necessary. All the primer cartridges have to be inserted deeply. Then workers bundle the fuses together.
The working face is now fully loaded. Our authorized explosive handler connects the explosive wires. And then we will move back to where we will be triggering the explosion and measuring the resistance, and then trigger the explosion. It's important that all equipment has been put in a safe place and the people are safe. The authorized explosives handler is actually the last person who looks to see if the tunnel is vacated and everything is in a safe place because he will be pressing the button. Thank you. Coupling, let's go. The ignition lead is the yellow wire. This is the extension wire which leads ahead to the electronic detonator, which then triggers the explosion.
The workers now have to move all the vehicles at least 150 meters away from the working face and stay 300 meters back themselves. Clear and precise rules are essential for a safe blast.
Nothing whatsoever should go wrong here. We try to work in such a way that nothing goes wrong in terms of the explosives. They are always difficult and dangerous, but we are drilled in this. We've been here for more than 2 years, and we've gotten well used to working with the rock, the bedrock, and the subsoil. So far.
The demolition expert is ready and awaits the explosion signal.
Blast triggered. Every blast is a special event, every round. It's always something special.
After each blast, no further work can be carried out at the working face for the next 20 minutes. First, a thorough inspection has to be conducted. Dispersal needs to take place. This is done with these 2 large air tubes, the air ducting system.
Here, fresh air is sucked in from above ground and pumped into the tunnel drive. In this way, the exhaust gases escape through the tunnel. We have to disconnect it properly before blasting because the pressure and the shock wave from the blast would result in vibrations that can cause this air ducting system to fall off. But by depressurizing, switching off the fan, then nothing will happen during the blast.
Georg Hofer goes up to the surface. He's expecting a supplier. They're allowed to continue blasting work until 10 p.m., provided there are enough explosives to do so.
We're getting some fresh explosives to be able to continue overnight. Every detonator, every explosive is scanned. It's like being at the grocery store checkout.
Grocery store. Twice a day we fill the construction site with explosive charge, early in the morning and in the evening. One of us has to be present on site at all times. The material must never be left on its own. An authorized explosives handler must always be present on the construction site, and this person is the only one who's permitted to carry out this job.
Blasting occurs 9 to 18 times a day, and 80 to 100 kilograms of explosives are required per blast. The nearby residents were therefore somewhat concerned at the start of the work.
Our neighbor directly behind our shaft is the company Daimler. To the best of my knowledge, manufacturers' model certificates are printed in this building, and they were initially afraid that we would create such great shocks blasting below that these approval certificates would be smeared or blurry. That is why we have to call them first when we are blasting. And in the meantime, we have a very good contact with our neighbors and an excellent relationship.
The atmosphere is tense on the construction site at the Albvorland tunnel. Today, the loading of the almost 12-meter-wide cutter head wheel has to work. It's the second attempt, and each delay costs money. The wheel is to be hoisted right over the site facilities to the pit. There, it will then be installed at the head of the tunnel boring machine. An electronics problem in the connection between the large crawler crane and its securing counterweight had made loading impossible on the previous day.
We still haven't found the right solution. We're improvising, as often happens in tunnel construction. Now we'll lift the cutter head wheel into position using an improvised ballast solution. That is, the ballast trailer you can see behind us, which has a jammed brake, will be taken off load and used as suspended ballast.
The electronics problem will only show up on the crane's onboard computer as long as the ballast trailer is on the ground and its brakes could be used. If the tunnel workers now elevate the entire vehicle, it would indeed no longer be able to brake. But at the same time, the blockage affecting the electrics would be circumvented.
This would be the quick solution.
Simply idling, more or less.
True.
Without brakes.
If the tires are also suspended freely in the air and cannot move independently on the ground, the crane operator will have no control. So when lifting, exact control of the ballast trailer is not possible. However, the securing function of the counterweight at least remains intact.
The engineers have calculated this, so it should work. It's always tricky finding out how much ballast I need to remove for the trailer to be suspended.
The engineers work feverishly on the spontaneous solution with the hovering ballast trailer. For this, a crane removes some of the 7.5-ton weights and sets them to the side. And the cutter head wheel and drive unit also have to be prepared for the new method of loading.
If the cutter head wheel is twisted, we'll have to turn the drive unit slightly to fit. Otherwise, installation and mounting will be difficult.
Simply hoisting across the cutter head wheel would be too dangerous. Even so, it remains a tricky and delicate operation for the specialists to deal with.
The problem we have at the moment is that everything has to be gauged. Preparation is everything. Then we'll hoist it round, and it must then fit perfectly at height from the flange, from the drive unit to the flange, from the cutter head wheel. And when it is in one axis, the cutter head wheel will be properly latched on with the flange from the drive unit. Precision work, to the exact millimeter, so there's no leeway in this.
Because the ballast trailer in its suspended state cannot counterbrake, it's now entirely up to the crawler crane. The crane operator has to hoist the wheel into the construction pit with extreme caution.
We're lifting the cut-ahead wheel into a very narrow place. The wheel itself weighs around 200 metric tons, so it's not very easy to move. This does require some manual intervention, positioning it in such a way that it can be inserted into this aperture, which we now have at the front in the pit. It's impossible to rule anything out.
Costing around 500,000 euros, the workers cannot allow for the cutter head wheel to strike or impact anything. The smallest amount of damage would impede functional efficiency. Once in place, the centerpiece of the tunnel boring machine is set to remove up to 20 meters of rock per day.
We need to turn the drive unit very slightly. It would also work like this, but it would be a little more difficult. We'd have to adjust the crane and work with chain hoist to pull in the cut-ahead wheel. If we get it into a good position from the beginning, it'll be a lot easier and save a lot of work.
Soon, the lift will get underway. Tension rises among the workforce and onlookers.
Yeah, it can start now. It'll be all right.
Wird.
Loading begins. The crane moves the first few meters, and to the rear, the counterweight is levitated along with its 170 tons, exactly as the engineers planned. The first rotation, the next few meters, everything is still holding. Maybe the improvised loading operation will actually go smoothly.
It's not going to stay this way. They're still working on a proper solution. The crane is not permanently in operation. We often have breaks and they can carry out the repair then. And I'd feel better if we were working with the usual configuration again.
In the first hour, the wheel is raised over the construction site. In order to be able to move the 1,200-ton crawler crane to the head of the tunneling machine at all, a stable platform first had to be built. The giant now moves ahead on this platform slowly and carefully.
This marks a milestone. We now have 1.5 years of preparation behind us. The machines are designed, conceptualized, manufactured in the factory, pre-assembled, dismantled, driven here, and then reassembled. And when the cutter head wheel is then hoisted into position, it makes for an impressive sight as these parts are airborne. And when they are installed, it marks the completion. This is just fantastic. And all the effort, all the blood, sweat, and tears, all the hard work has again been worth it.
The ballast trailer performs its job, raised off the ground. Now the cutter head wheel can be lowered down into the shaft. Minimum final turning is required by the workers, with muscle power, and then it's lowered straight down. After precisely 2 hours, the cutter head wheel with its 140 spade cutters is in its designated position, right at the head of the huge tunneling machine.
The drive unit was tilted at precisely the same angle as the cutter head wheels attached. Flange on flange, 0.01 degree of difference, and that is really important. Because if you have two different angles of this part, where we are mounting from the cutter head wheel to the flange, where it is bolted on, the angles have to be exact, just as the direction downwards in the alignment. And it has worked fantastically well here now.
Tunnel driving can get underway shortly with the cutter head wheel.
A job like this is not something everyone has. It's a great feeling moving a component weighing more than 200 metric tons and then installing it. Absolutely unique. It's a feeling you can't describe.
Further blasting work is being carried out in the urban tunnel construction site in Stuttgart. The resulting excavation material is cleared away by wheel loaders, which tip it onto dumper trucks. These are large, robust, and above all, very flat transporters which are ideal for moving in narrow tunnels. A dumper truck can take a load of 30 tons. The rubble is delivered to the access tunnel. Wheel loaders tip it into the debris collector to transport it out of the shaft. All the vehicles deployed here are very heavy and robust. However, on occasion, something can break in an operating area such as this. Usually, it's the tires. If the repair cannot be carried out on site in the tunnel because of large amounts of dust or noise, the vehicle, like this transporter, has to be hoisted up and taken to the construction site workshop. There's always some broken machinery being stored here.
The drill is currently without its transfer case. It was worn out and needs replacing. Here we have a lifting device, a Manitou. Tunnel transport vehicles always have some engine damage, minor faults, flat tires, etc. At the back there is a small excavator which we are using for the crosscut. It is also currently being welded because it is cracked.
For each type of vehicle, there's at least one spare tire available. However, it's not just the tires. The workshop is needed around the clock.
Good luck. This is our daily operation. You have to remember, we have more than 60 large units operating below at the cutting face. We need approximately 2,500 liters of diesel for these large units every day. We have a diesel tank station and we hoist it into the shaft in small quantities and refuel the vehicles, maintain the air filters, lubricate the moving parts, and so on. So there is a dedicated crew maintaining and refueling these machines.
The electrical mechanics work at the rear in the workshop container. Electronic components constantly break down at the tunnel construction site.
One section's intact and the second is worn away.
Obviously, our electricians have a layout of how our structural engineering works. It sets out the precise location of the transformers, where the power supply is, where the ventilation is, etc. So it is possible to know right away, we have something here, we can get the power from here, etc.
In the case of urban construction sites, such as here in Stuttgart, there are restrictions for noise and dust. This complicates the tunnel builder's work. In addition, at 12,500 square meters, the area at the surface is relatively small.
We just about manage here with the size of our site setup area. Here we have our on-site mixing plant at the back. This has the advantage that we can supply cement and gravel during normal working hours from Monday to Friday or even Saturday during the day. And we're allowed or able to produce concrete 24 hours a day, even Saturday and Sunday. We also have here the storage area for our support material. Here we have steel mesh, lattice arch girders, and over there are rock bolts and spikes. Everything we need. We need to have plenty of supplies of everything so that if something unforeseen happens down below, we can simply manage the situation and at least have the support material in place.
The numbers on the stored components help the forklift and wheel loader drivers to have direct access to the correct sizes. The Austrians lead the way in tunnel construction and have the best qualified personnel. Georg Hofer comes from Styria, where he studied mining engineering.
At some point during my studies, I came across tunnel construction or mining. I had already been working in deep mining and have now been on large construction sites for over 20 years. Anything that involves a tunnel construction site, or a tunnel at least. And sometimes I wonder what motivates me. There's always something new. We get to go places where no one else has been. That just fascinates me.
The team around Georg Hofer has to build nearly 13.5 kilometers of tunnel from Stuttgart-Wangen, and they have already made considerable progress. The first link to Wagenburg Tunnel at the main station has been established after around 2 years of building work. Soon, trains will really be able to enter the Stuttgart station, and not just like in the animation. Reinhard Pankratz is Georg Hofer's deputy. He oversees line 714, which has now been cleared for excavation material. Now, the workers position the earth with a semicircular iron structure, attach mesh to the introduce, and seal everything with thick shotcrete.
The purpose of shotcrete is to absorb the rock weight and prevent distortions in the rock. That's necessary, of course, when we're working in urban areas in order to protect the working tunnellers from falling rock or any loose parts. And then the second location is lined and again shotcrete is applied. If required, face anchors are set out, which are these iron components you can see in the background. They're used to stabilize the working face.
5 for number 1.
The tunnel workers put the arch in place with the aid of a lifting platform. The tunnelers at the front install the elements exactly in line with the foreman's adjustments on the angle measurement tool with centimeter precision.
Okay.
The shotcreting rig applies the concrete. The compound is mixed directly on site and can be used immediately.
It's important that the density of the shotcrete is correct. The first location is sprayed with 20 centimeters, then lined, then a further 10 centimeters is sprayed on. The entire process obviously takes place under time pressure because we need to ensure that work is carried out in a timely manner.
Speedy operations continue here 24 hours a day, Monday to Sunday. There are short breaks, only at Christmas and Easter. Otherwise, no downtime.
A principle of Austrian tunnel construction, also known as shotcrete construction method here in Germany, is simply continuous driving to allow the newly sprayed shotcrete at the front to undergo certain distortions. Rather than this stop-and-go operation over a weekend, when I put my tools down on a Friday and don't start again until Monday when the shotcrete is already hardened. This is a key principle. And construction time and investments in equipment have to be fully exploited. This is why there's 24-hour operation all year round.
Quick progress is also being made in Kirchheim unter Teck. The Albvorland tunnel is being built here with Wanda, one of the 2 tunneling machines. Sibylle, which was installed at the same time as Wanda, will very soon be up and running as well, creating several meters of tunnel tubes daily. After a week of driving, the team has advanced just 23 meters, which for site manager Katrin Haas is not yet satisfactory.
The first few meters proved to be very difficult. We still had initial problems with the individual components, with the whole construction field, be it the machine, the conveyor system, etc. But for the past 2 days, things have been going ahead nice and continuously.
The 2 tunneling machines are very close to each other. They cannot drill simultaneously, since the shocks would otherwise be too great, particularly here directly adjacent to the freeway. In tunnel construction, it's always a matter of avoiding subsidence. In other words, elevations or depressions at the Earth's surface. Thus, Sibylle, which was installed in an equally complex manner, will only begin when Wanda is much further ahead. In terms of their construction, the 120-meter-long tunnel boring machines are identical. Each weigh 2,300 tons. While the cutter head wheel at the front excavates through the earth, to the rear there are 6 trailers on which the entire plant is installed. On the steel construction, there are hydraulic units, pumps, ventilation systems, laser measuring technology, and the storage tanks for the soil conditioning agents. Behind the drill head of the tunneling machine, soil is collected and transported on long conveyor belts, initially out of the tunnel and then over the entire site. The machines operate in so-called EPB mode, or Earth Pressure Balance mode. Here, the workers can add various liquids to the soil at the working face to make it easier to dissolve.
Here we can see our excavation material. EBP mode also means that we now condition our material. In other words, the excavation material is mixed in the pre-cage at the front with foam agent and water. And this is why it is now so fluffy.
The excavation material is conveyed to the drop tower, mixed with lime to reduce the water content, and then loaded onto trucks which bring the spoil to a trash dump. Next to the tower is the provisioning area on which the workers are constructing another conveyor system.
Conveyor 130 is currently being pre-assembled here, and it's being raised at noon today. These are machine components which are supplied like this and then installed and fully assembled. Since we're starting with one machine, it's actually quite normal that final routine operations are still underway for the second machine.
After the setup is complete, the conveyor system is connected at a height of more than 15 meters. Then, the second machine can begin its work too. There are two phases in tunnel construction which follow one another continually: heading and ring erection. Circular segments are used for the ring, which are later installed on the tunneling machine in a circular fashion. They form the inside wall of the tunnel. Using a special app, Katrin Haas calibrates online whether the individual components, known as tubbings, have been released for fitting.
These tubbings then result in our ring. And a ring we are building on the machine consists of 7 tubbings going from block A to K. The respective shift engineer must always order the appropriate ring, since we have left and right rotated rings here, and also 15 special rings.
Before the ring-shaped tunnel tube comprised of nearly 5-meter long and 2-meter wide tubbings is assembled, a crane has to pre-sort them. Everything is still in the early stages here.
We store our tubbings here, which we also produce on the construction site. They are just arriving in piles of 2, and are then stored here in the area behind me. When the area is full, up to 10 pieces will be stored, one on top of the other, and we have 3 stocks of them, with room for a total of 950 rings.
The selected tubbings are loaded onto the multi-service vehicle, or MSV for short, which will then bring them to the tunneling machine. Precise work is key in order to not damage any of the 10-ton concrete segments during transportation, and make sure they are ready and available for the next stage of the work. The team can still take its time.
When we actually have both machines carrying out excavations and we are further along in the hill where the routes then continue, we expect to have 4 MSVs per tube, even ones that are larger than these here. And they will actually drive in and out in the tunnel non-stop in order to be able to work the machines without waiting times.
While the conveyor belt 130 is hoisted into position on schedule, the MSV fetches 15 cubic meters of fresh mortar from the mixing facility on the construction site. Just like the tubbings, mortar is also required in the tunnel boring machine. Tunnel boring machine Wanda is comprised of several stations. The MSV approaches with the fresh mortar and the tubbings. The binding agent arrives in the tank on the machine via the mortar transfer pump. A worker who operates the segment crane takes care of the tubbings.
It has a bearing load of 11 metric tons, and it is used to unload the tubbings from the MSV and to hoist and bring them to the front of the machine and then deposit them on the feeder. That's the feeder, that's the track transporter, which then presents the rings to the erector. Until everything is working well, we are likely to have 8 to 10 rings per day. In other words, 8 times 7.56 individual tubbings.
At this point, the tubbings are inspected one final time before being passed on to the frontmost station of the tunneling machine, the erector. The tunnel tube, which has a diameter of more than 9 meters, is then assembled out of the concrete elements. And this is how, what the tunnel builders call, their ring is created. The area between the exterior formwork of this ring of tubbings and the rock is subsequently filled with mortar. In the next station on the tunneling machine, a worker is sitting directly at the mortar transfer pumps.
I enter the pressures here, the bar pressure I'm injecting. You can see the figure with how many bars it will be pressed to become hardened.
While mortar is pumped behind the exterior formwork, a colleague at the front on the erector is busy cleaning before the next tubbings are inserted. Everything has to be kept clean. The erector is supplied with blocks by the segment feeder. Hydraulic presses retreat at the corresponding mounting position. Then, a worker places the particular tubbing via remote control. This is how the tunnel ring is created.
The erector can perform 3 movements. It can go forwards and backwards. It has to do so in order to suck in the segment from below by means of a vacuum, and then has to travel onwards to the deployment site. It needs to turn to be able to place the block in all positions, and of course it has to be able to tilt in order to be able to attach the block exactly.
The ring consists of 7 concrete segments, which are inserted one after the other by 3 workers. One of them being the erector driver, who operates the complex machine. He sucks in the segment and positions it in the right place. The other 2 are the ring builders, who calibrate each tubbing precisely.
This is truly precision work here. The ring is only allowed to have a maximum offset in the longitudinal curve of around 7 millimeters. If we don't manage this now, we would have to dismantle the segment again and reposition it. This is actually the heart of our machine, right here.
If a 2-meter ring has been set as completed, the tunnel will be advanced for 30 to 45 minutes at a maximum speed of 90 millimeters per minute. Heading and ring erection, these are the 2 main steps. They follow one another continually. One sequence should be completed in 1.5 hours, and then it starts all over again. During tunneling, the machine operator must pay attention to the earth pressure with the so-called bulkhead and the composition of the stone in front of him. Often, there are very different areas which the machine travels through. At the moment, there's a lot of clay and sandstone.
These are just the revolutions from the bulkhead. Here I can see my power consumptions, that the bulkhead doesn't block, that it's not turning well. I need to top it up with a certain quantity of foam to turn it into a creamy paste so that excavation can take place.
Site manager Katrin Haas has ambitious targets. She wants to create more than 10 rings per day.
We will try to exceed the 20-meter mark a day in any case, but this is not scheduled to happen until we are operating in the so-called open mode. That means we no longer prop up the working phase with earth paste, but instead it runs unsupported. And then we will try to speed things up.
600 construction workers and 80 engineers and geologists work in the Albvorland tunnel to make sure that just like the tunnel site beneath Stuttgart, soon here too, there will be light at the end of the tunnel.